here from CDPG. A warm welcome to today's data dialogue session. The topic of today's talk is machine learning for geospatial data processing in earth sciences. In today's world, LULC or land use land cover change is driven by natural process and anthropogenic activities, which remain a key focus area in earth sciences, where we go through a lot of satellite images to classify it, and wherein machine learning comes in handy. Leveraging machine learning techniques to process such large-scale satellite spatial data set allows us to better understand and model these transformations at regional and global scales. With that said, it's my great pleasure to introduce our speaker, Dr. Uttam Kumar, Associate Professor in Department of Data Science and Artificial Intelligence at IIIT Bangalore. Dr. Uttam has earned his PhD in algorithm for geospatial data analysis from IIC and Masters in Geoinformation Science from University of Twente, Netherlands. His technical expertise spans spatial data mining, machine learning for scientific application, and Earth observation analytics. At IIIT Bangalore, he convenes spatial computing laboratory and serves as associate faculty in Department of Computer Science and Engineering. Before joining IIIT, he served as a NASA postdoctoral fellow and visiting scientist at NASA Ames Research Center in California, later as a researcher at Stanford University School of Medicine. Over his career, Dr. Uttam has published more than 150 research papers and book chapters and delivered over 100 invited talks at national and international forums. His contributions have earned him several prestigious awards, including National Geospatial Award in 2021, Young Engineers Award from Institute of Engineers, India, multiple Best Paper Awards across major conferences from IITs to NASA affiliated events, and the highly regarded NASA Group Achievement Award. As a leading voice in spatial data science, Dr. Uttam's work bridges the discipline of geoinformatics, data science, and Earth system modeling, which aims to make geospatial intelligence more computation driven and socially relevant. With great pride and anticipation, I now invite Dr. Uttam Kumar to deliver his talk. Over to you, sir.
Thank you very much, Linda, for the warm invitation and also for the introduction. It is my pleasure to be here today and share some of our experiences working on geospatial data processing in the data dialogue program at Data for Public Good at IISc. Uh, I would be very happy to start the talk. I am basically trying to cover multiple smaller projects and larger projects in the presentation, and also at the same time would like to give some theoretical background so that the audience is able to cater to the mainstream flow of our geospatial data processing with applications in Earth observations. So at IIIT Bangalore, we have a GIS lab, also known as Spatial Computing Lab, founded with a generous contribution from Infosys Foundation. And we work in different areas of spatial data science, urban informatics, agriculture technology, remote sensing and GIS, spatial computing, time series forecasting, applied AI and deep learning, and so on. And currently we have some projects from different organizations and a number of MTech, MS, and PhD graduates. Also, some lab interns from across the country, lab alumni, etc. So, the main focus of our lab is to work on geospatial computing and many allied areas in this particular domain. These are some pictures I am happy to share from our department and from our spatial computing lab, and one of the most prestigious workshop was held in collaboration with NIAS, National Institute of Advanced Studies, where we see Dr. K. Kasturi Rangan, the late Dr. K. Kasturi Rangan inaugurated the event, and then some pictures of our meeting with ISRO scientists working on different agriculture related projects. So this is our lab website, Spatial Computing Lab, where we have provided all the other details related to publications, current projects, completed projects, and so on. And at the institute, our focus has been to work on spatial data science with applied machine learning and AI. And a broader domain of GIS is also a part of our day-to-day activities at the lab. Since most of the spatial data is related to satellite images, so we obviously use a lot of digital image processing and subsequently try to maintain database for most of these applications. So on a very specific applications level, we have looked at some of the very local to global problems relating to urban sprawl, urban mobility, and crop classification in horticulture, in agriculture farms, tree detection, and global vegetation cover. And in towards AI related applications in geospatial domain, we have looked at scalable machine learning algorithms, imbalanced learning, and so on. Okay, so these are some of our recent publications which I have grouped into different themes. In the urban area, we have worked on urban patterns in both small and medium-sized cities across the country. We have looked at urban road networks and road hierarchy topology, and also we have worked on land cover estimations using different methods. One of the very close problem that our society currently is facing is related to different types of epidemics, for example, dengue or malaria. And some of our work have focused on forecasting models, time series forecasting models based on different climatic conditions that impact or that has some influence on these epidemiological studies, such as dengue outbreak or other diseases across our country. In the image and data classification domain, we have worked on different types of problem. For example, in the agriculture domain, related to plant classification or plant disease detection, working on ML models for imbalanced learning, for uh, for data oversampling, for continual learning. So here are some publications that I have just stated. And in the geospatial domain, we have worked on some very specific problems. For example, satellite image to satellite image co-registration, automatic co-registration, or working on data privacy or in machine learning, and some applications related to local problems, for example, pothole detection and so on. So in this talk, I will be focusing on some of these problems and some possible solutions um, for working with these particular data sets. But before we get into those very examples and specific applications, I would like to draw your attention to our current motivation that has helped us to get into this large scale geospatial data science. So we all know that currently it is the field of statistics that has been constantly challenged by the different problems, either related to growing data volume or the human limitations of analyzing these large data sets, etc. So currently, most of these problems are not exactly related to computer science, but more often than not, they have their origin from statistics. And this problem is widespread not only in academics but also in scientific community and also in the industrial settings. So we take advantage of our low cost machines and try to explore these problems, where these problems have actually exploded both in size and also in complexity. So the greater challenge in front of us is, given this large data volume, how do we store all this data, how do we organize all this data, and how do we look for certain important patterns from the data. Together, the storage, organization, searching for pattern, retrieval of patterns have led to the field of spatial data science. So data science is actually an end-to-end solution to any given data problem, which starts from data collection and then moves on to data cleaning, data integration, data selection, and data transformation. And very often, all these steps are considered to be part of data pre-processing. So the nature of the data pre-processing is to help us to make the data analysis ready, and very often these data pre-processing tasks require significant amount of our time. However, it is then realized that the actual data analysis has yet to start, and that is what we are trying to do in our different research paradigms. So data analysis in earth sciences, or irrespective of the application in other domains also, typically deals with data mining, where the idea is to use some scientific methods or algorithms or processes and try to extract some hidden useful non-trivial patterns from the data. So these hidden useful non-trivial patterns that we would like to explore or we would like to extract definitely is of very high importance, because they reveal several important trends and patterns that are not easily visible in by looking at the tabular data. So in some sense, they help us to extract knowledge and look into the insights from these from the large data sets. These data sets can be either structured or sometimes they are actually unstructured. All right. So I was talking about some of the large data sources, and few examples are remote sensing satellites in the space that typically keeps taking pictures of the Earth's terrestrial surface, or telescopes scanning the skies, or gene expressions, or scientific simulations that generate terabytes of data. Now, the term data analysis that we have just now used is not something very new. If we look back and see some of our old statistical books, they often talk about univariate and multivariate data analysis, and there are established techniques to perform data analysis. So, the challenge now is that most of these techniques have been developed with certain assumptions, for example, assumptions of sample size or distribution. And currently, we often encounter large data problems or big data problems. More often than not, these big data do not actually fit the assumptions of our traditional statistical tests. Therefore, we use some learning methods, machine learning methods, that can narrow down the data size, either through classification or through clustering or through segmentation. And then on these small classified data or cluster data or segmented data, we try to test our statistical hypothesis. So, what is the challenge in all these problems that we have been looking at is to make sense of all these data, to extract some pattern, or to get or to obtain some trend from the data, and we try to understand what the data says. So, this is what we call learning from data. Okay. Now, we are all very much aware of the term machine learning, as we are using it almost in our day-to-day research. So, machine learning typically talks about a collection of several algorithms or computer programs that automatically try to improve with learning and with experience. So, here machine learning, we try to view machine learning from multiple perspectives, and the idea is to understand the problem itself, the problem settings, the algorithms, and the assumptions that underlie each of these different applications. So if statistical analysis has been there for a long time, a very important question is how did this statistical learning evolve over a period of time. We see that at the beginning of 19th century, Legendre and Gauss published their first papers on methods of least square, which is very much used in linear regression. In 1936, Fisher proposed the linear discriminant analysis. In 1940 came the logistic regression, which is a very well-known technique in machine learning. In 1970 came the generalized linear models, in 1980 nonlinear models, and mid-1980s Bremen and Cutler introduced the CART, that is classification and regression tree. Close to 1986, Professor Hastie and Professor Tipshirani from Stanford University, they coined the generalized additive models, and then onwards, the term statistical learning gained more focus, and slowly the term machine learning gained more attraction in our community, and now we know that the term AI has taken over, where everyone now talks about AI and their applications. So a bigger question is, what is the learning that we try to do in ML? So think of a simple AI application or an ML application where the application is a software deployed in a hospital, and the software passes through different patients' medical records and the treatments, corresponding treatments given to these patients. So based on this learning of the different records, can the software identify a new disease in the future, and can it also suggest appropriate treatment? Or think of another example. For example, for as such smart homes or smart offices, where we try to make those houses smart because the houses learn from experience as to how to optimize the usage of natural resources or natural energy. That could be either electricity consumption or water consumption, etc. So, or we currently have also witnessed several examples where we see smart washing machines, smart lighting systems, which are often connected through IoT, and a person using a mobile device can can use those appliances at their will, and also at the same time optimize the energy cost. Third example is very common, that talks about personal software assistant, for example, Google Assistant, Alexa, etc., where these systems try to learn from the way we interact with them every day, and then they help us in multiple ways in our day-to-day life, right away from helping us with the current traffic situation while we are going to office, or updating us with the weather report, suggesting to carry an umbrella if it is likely to rain, and so on. So, in all these three examples, we see the word learning in different context. And it is important to see that in these three examples and many more such examples that we can continue to list, our concern is not to analyze the meaning of the meaning of English word learning. Rather, we are more interested in defining a class of problems that encompass interesting forms of learning. That encompass interesting forms of learning, and in this process, we try to explore different algorithms. We try to understand the structure of the problem. We try to understand what is the process running behind these problems, and so on. Let's see some more example. So we have a AI ML based software, typically in a hospital, that passes through a patient's records, and it looks at the patient's demographic data, diet plan, clinical measurements, and let's say the patient has suffered a heart attack. So can our AI model predict, based on the data, demographic data, diet data, clinical measurements, whether the patient is likely to have another heart attack? Or think of another ML-based software that can predict the price of a stock in 6 months from now, based on the data of company's performance measures or economic data. Another AI example could be identifying the numbers written in a zip code or pin code on an envelope, and this is a there is a digitized image of the envelope, and the AI/ML application is able to read those pin code and reroute the envelope for the destination. So the idea is to automate this sorting process so that the delivery of the envelopes are faster. Or the fourth example, where we use some AI tool to estimate the amount of glucose in the blood of a diabetic patient, maybe through some technology like infrared absorption spectrum of that person's blood. So in all these four examples that we have seen, we notice that the word predict, identify, estimate, etc., occur very frequently. So these few words, they actually help us to decide what is the nature of the machine learning problem and what could be an appropriate set of algorithms or techniques that can be used to predict something, identify something, or estimate something. So broadly, most of the machine learning algorithms will work either as a classification task or for a prediction task. In the classification task, the idea is to use an algorithm, a classification algorithm or a ML algorithm, and also use a data called training data. So training data is a tabular data, which is some observation or measurement, and this observation or measurement also has a corresponding class label. So the algorithm will learn this training set, that is the observation, along with the class label, and hence it will come up with a model. So my model is ready by the time the classification algorithm has learned the training set. Once my model is ready, if a new data point arrives, we can look at the characteristics or observations or measurements of the data, and the algorithm can then predict the class level. So here the idea is that based on the developed model, the classification algorithm is able to assign a class label to every set of data points in the test data. In prediction, we try to model continuous valued function. For example, there is a well-known technique called linear regression that is very often used in predicting unknown value or predicting missing values. Within the realm of classification, the techniques are either supervised learning or unsupervised learning. So, as the name suggests, supervised, the idea here is to develop the model based on some data that is called training data. So this training data consists of some observations or measurements accompanied by the class label. Class label could be something like A, B, C, D, E, 1, 2, 3, 4, 5, blue, green, red, anything, some categorical class label. And once my model is ready, as I said earlier, it can be used to classify new data points. So we see that the model here or classification algorithm here has learned under the supervision of some data called training data. Therefore, these are known as supervised learning methods. On the other hand, in unsupervised learning methods, we do not have a training data. So only tabular data in the form of observations or measurements are provided. And the idea is to naturally group these data points based on some criteria, based on some observation, based on some or a set of measurements. So here typically we get a few groups, we get some few groups, and then we, for example, this is my group number one, group number two, and I would draw one more group, for example, group number three. So it is the role of the analyst to find out what is group one, what is group two, and what is group three. So these groups are different from one another and are very often also known as clusters of points. Therefore, these algorithms that perform unsupervised learning are also known as clustering algorithm. We see that in clustering or in unsupervised learning, there is no supervision, there is no training data. So since there is no training data, there is no supervision, therefore these are also popularly known as unsupervised learning. Okay, so now we see some examples. Autonomous vehicles that are now very common in many countries uh, are, are able to move without any assistance, without any driver. So before they became expert, before they became autonomous, a trained driver used to take these cars along different roads, different highways, in different traffic conditions, in different weather conditions, and on different types of internal roads, city roads, highways. And there is a sensor on the top that keeps taking pictures of the surroundings. So based on the surrounding scenario, the driver helped the car to learn, saying that if the signal is green, speed up. If the speed limit is 60, speed up and maintain 60. And the algorithm has slowly learned that given this scenario in the neighborhood, take this action. So this is an example of a supervised learning where the car over a period of time has learned with the help of an expert driver how to move on the road autonomously. So now the car is as expert or even better than human driver because they don't get tired, and as a result they can perform the task independently. So this is an example of a supervised learning task where the car has learned under the supervision of an expert driver. This example is a world map shown in white patches with a blue background. This example shows approximately 1.1 billion people who use Facebook. So this map was generated in October 2020 by Facebook themselves, and they wanted to look at the distribution of people across the world who use Facebook. For example, eastern part of North America, eastern part of South America, UK, Europe, India, Southeast Asia, Australia, New Zealand, Japan are the leading countries where we have large number of people using Facebook. Now, this particular map has been generated by one of the parameters that we have provided to Facebook, that is our location. So our location has been converted to latitude, longitude, XY, and has been then used by a unsupervised learning algorithm called DB-scan, density-based scanning technique, density-based scanning technique to generate this clustered output. So this map is very, very useful for several reasons, including promoting the sales, advertisements, and so on. And we see that India, United States, Indonesia, Brazil, Mexico are top 5 leading countries where we have maximum number of people using Facebook. So this is an example of data clustering, or to be more specific, it is an example of spatial data clustering. All right. So to summarize, we have seen that supervised learning can be of type regression or classification, where both have labels. Regression has continuous labels and classification has categorical labels. And unsupervised learning is called clustering, where we do not have a label, rather we have groups, and we try to assign some label to each of the groups based on our experience or based on the domain expert advice. Linear regression is one of the most commonly used technique for predictive analysis model, as a predictive analysis model. So if we look at this particular slide, we see some pattern. There is a football and then a stationery with some pen and pencil set, again football, and then again a stationery. So now here the question is, what comes next? What comes next? So this is a typical prediction problem. So we need to identify that this is a prediction problem, and we will have to choose an algorithm that is able to predict predict in future, future in the sense the next what will be the outcome. This is another example where we see two classes, class 1 and class 2. Class 1 has three square boxes. Each square box has two black box, two white boxes, and we see that the black boxes are arranged diagonally from left to right or right to left. In class 2, we see another three square boxes, and the black boxes are arranged in a vertical or horizontal manner. Okay, so we then uh, show a new box which has not been shown earlier either in class 1 and class 2, and ask, what about this? Would you like to place it in class 1 or would you like to place it in class 2? This becomes a classification problem. This is the typical classification problem. So earlier we saw a prediction problem, and now we see a classification problem. This problem can be extended, and we can show several cars of different make and models, and then show a new car and ask, what about this? Or we can show several pictures of airplanes and then show a new type of airplane and ask, what about this? So these are all classifications problem where we try to assign a class label to any new data point. Finally, we realize that uh, there are three important essence of learning. First of all, it's very, very important that there has to be a pattern in the data that we are looking for, and sometimes it's possible, sometimes it is difficult to capture these patterns in the form of a mathematical expression. Thirdly, we should have large amount of data to come up with these interesting pattern. So we realize that seeking a process or finding a process that can look into, that can capture these underlying patterns that we have been talking about, these underlying patterns without we explicitly telling it out, is called learning from data. And that is what we have seen in some of our examples prior to this particular slide. Okay, so one important question here is, how does the model remember that it's an aeroplane or it's a stationary or it's a football or it's a earth? So let's take one simple example to make sense of what is happening here. We have two classes, class 1 and class 2. Each class has three sample, sample 1, sample 2, sample 3, sample 4, sample 5, sample 6. Each sample has two black box and one white box in class 1, and each sample has two white box and one black box in class 2. Okay, so now we would like to learn this particular pattern by a machine learning algorithm. To do this, we first derive a feature from the samples. So let's say here number of black boxes could be one type of feature, one type of observation. Now let's plot this. So I have training sample number 1, 2, 3, 4, 5, 6 on the x-axis and number of black boxes on the y-axis. Automatically something emerges. These data samples quickly align themselves in some order based on the data characteristics, that is the number of black boxes. So we see that we have two dimensions here. One is training sample number, that is x, and then we have number of black boxes, that is y. I could even add the third dimension z, that is number of white boxes. So any data point that we plot here is called a sample instance, and it has a corresponding value on x-axis, y-axis, and z-axis. And the space where we try to plot this sample instance is called the feature space. It's called a feature space. So for a given sample instance, we have three values of feature 1, feature 2, and feature 3. From this, we try to derive simple rules, simple English rules. For example, if a new sample arrives, what to do? How will I place it in class 1 or class 2? So if a new sample arrives, do as follows. Compute number of black boxes. If 1, put it in class 2. If 2, put it in class 1. So by looking at the feature characteristics observations, we have been able to develop simple English rules that allow us to classify objects into either class 1 or class 2. Fine. So the problems in earth sciences can be of two types. Sometimes it's very simple when the things are linearly separable in case. So I just need to come up with a equation of a line that can separate the two different types of shapes. Sometimes or many a times problems are non-linear separable, where a simple line cannot discriminate the two different types of shapes, the blue one from the gray one. So we may require a polyline or a polynomial. Uh, um, as we see here, the red color curvilinear feature, which will be required to be drawn by the machine learning model in order to separate the blue and the gray symbols. So obviously, it is true that non-linear separable cases are slightly difficult to solve because of the complex boundary requirement at the separation level. So we realize that in terms of statistical learning, we are actually trying to find one optimal solution. We are actually trying to find one optimal solution in the solution space. So typically in a solution space, it's possible that we have more than one solution. And out of those multiple feasible solutions, we try to get or we try to find the optimal solution. Optimal solution. This optimal solution obviously will very well fit the training examples and any other constraints that you have. So in earth sciences, we have different types of constraints. For example, there is a rule or act saying that we cannot have any construction activity within 500 meters of the lake bed in cities. So this is a constraint. So the optimal solution will be not only able to fit the training examples, but it will also be able to meet any real world constraints. Okay. So we move on and just very quickly look three important issues in machine learning. One of the problems that everyone faces is after having tried or worked on multiple algorithms, it is still hard to decide or to conclude which algorithm performs best for what kind of problem and in what kind of representation in what settings. More often this is intuitive and sometimes it's experimental, so it's very heuristic in nature. Second important issue is how much training data is sufficient, and people have been working a lot on this training data, sample size. So there are still a lot of research going on to address this problem. This problem has led to a new series of challenging objectives in machine learning, including data imbalance problem, where we see that one class typically is heavily represented compared to other classes. So how do you then bring a balance in the sample size? We have done some work in this area, and still there is a lot of scope for improvement. The third important problem is how can you alter or how can a learner automatically alter its representation to improve its ability to represent and learn the target function. So this problem in some sense connects us to continual learning. So typically data sets that come in chunk, um, for example air temperature or wind speed, which keeps coming or which is observed every now and then. So these are called data stream data stream. Now we see that most of our machine learning algorithms are designed to work on data snapshot. But what happens if your data keeps coming all the time? For example, temperature, it's measured every minute, every second, every hour. So how do I develop a learning algorithm that can evolve with the evolving or with the changing data stream? This is broadly discussed in the realm of continual learning, which is again a very new topic and very interesting topic. Lot of work is currently going on in how to handle data stream through continual learning algorithms. Okay, so now I will switch back and then get into demonstrating some of the case studies. Okay, so we now proceed further and bring some relevant learnings from some of the Earth observation applications. I am trying to present here some work done on three different broader areas. One touching urban science, the second looking at land cover classification, and the third looking at some aspect of machine learning, where we focus on data classification, continual learning, and imbalanced learning with some relevant case studies. So let's start with our urban science problem and see some case studies done by our research scholars. So we all know that we live in two worlds. One is a natural world, other is a constructed world. Natural world is very often self-regulating, where which is consist of rivers, urban systems, mountains, forest, and rainfall, and so on. And the constructed world is has been the world that has been modified or altered by humans. So we have constructed buildings, large scale bridges, road networks, and so on. And in some sense we have tried to disrupt the natural world. So as such, since we have disrupted the natural world by carrying some activity, maybe with the focus on development, we see that these new changes on the Earth's surface have broadly brought some conflict between the natural world and the constructed world. So we look at two different scales while trying to solve problem on the earth as a system. One is trying to look at the whole world, and then by looking at the whole world, can we draw some patterns, can we draw some linkages, can we draw some trends? And if we look at a local level, maybe a city or a community, then try to address few things at a community level or at a neighborhood level or maybe at a district level. So GIS is a very important important area of, or it's often actually a very vast area, and there are masters level complete courses in GIS, masters in GIS, for example, that teach us many different aspects in which GIS is helpful to us along with other relevant domains. So GIS broadly tells or helps us to link geographic information, which says where things are. So more important here is the description where means location, and we try to attach this information of where with some description, that is what things are. So the two important aspects in GIS is where and what. We see one picture here where we have multiple layers of information that try to mimic the reality or the real world. So we have the real world at the bottom, and then we segregate or separate street layer, road layers, building layers, customers layers. All these streets, buildings, customers are independent layers, and they represent some theme. Therefore, they are also known as thematic layers. All right. So, very important question is, what is the benefit of using GIS? What does GIS answer? On a very broad level, GIS has some answers some very important questions. For example, what is at is a locational question. What is existing at a particular location? Or where is it is a conditional question. So these are typically questions like which locations satisfy certain conditions can be answered through GIS. How has it changed? It could be any object, it could be any field. So this is a trendy question. We are trying to see how things have changed, or we try to identify geographic occurrences over a period of time. Fourth question is which data are related. So we see that this is a relational question. We here we are trying to associate any spatial relationship between objects or between different geographic features. And the last one is perhaps the most interesting, where we use GIS and ask questions. What if something happens? So these are model based questions which typically help us to generate scenarios and then say, if this happens, this could be the scenario. If it rains for continuous 8 hours in Bangalore city, these are the areas that might get submerged inside water. So similarly, various models can be built for fire risk, for earthquake, for example earthquake, or for disaster management, for a flash flood, and several scenarios can be generated and visualized to realize what will happen if it rains for 8 hours, if there is a landslide, if there is a wildfire, and so on. So now I will just show you one quick example of a GIS from our one of the case studies, where we try to answer what is at a given location, where is it, and how has it changed. This example relates to our natural sense of perceiving the environment. So we have all seen or have witnessed these kind of scenic places around our city or country, and have very often visited and would also like to visit again and again. So these are all our natural resources provided by earth, and these resources often occur naturally. For example, land, water, forest, and so on. We have also seen that because of developmental activities, there are disturbances in these natural resources, and therefore we need some amount of planning to ensure that the development happens in a sustainable way. In this context, there are two very important terms that is very often discussed in the space community, that is your land cover and land use. In fact, most of the Earth observation missions by ISRO or by NASA or by European Space Agency, their premise has been to observe the land cover and land use change across the Earth. So land cover refers to the physical or biological cover present over the surface of the land. Could be water, could be vegetation, bare soil, forest, etc. Land use, on the other hand, is defined from human perspective as to how humans utilize the land. That is, the purpose and the context behind using a land. It can be agriculture, for agriculture purpose, for forestry purpose, for building construction, residential use, commercial use, and so on. Together, the term land cover and land use has been coined as LULC, that is land use, land cover. And changes happening because of change in land cover and land use is addressed as LULC change. We have currently witnessed and we are still experiencing a land use, land cover change across the globe in all the countries. And most very often, the reason behind this is human modification of the Earth's terrestrial surface. So these are very common pictures we have seen even in Bangalore city, where large scale farms have been converted to real estate buildings, lakes have been encroached and have been converted to high rise building. And then there are several detrimental effects of all these land use, land cover change, including global warming and consequent climate change, pollution of water, biodiversity loss, change in precipitation pattern, alteration, high intensity flood, groundwater depletion, and so on. So we realized that in order to address these problems, we may have to study the LULC change, the land use land cover change, especially for management practices, and also to mitigate and adapt to these changing situations, so that we come up with some solutions to some of these problems. This problem of LULC change and LULC dynamics has also been identified in several research agendas across the globe. So the remote sensing technology that typically captures images of the Earth surface at regular intervals are characterized by four different types of resolutions: spatial, spectral, radiometric, and temporal. Spatial refers to the size of the pixel corresponding to the ground coverage. So it could be, for example, 1 meter by 1 meter pixel, 10 meter by 10 meter pixel, and so on. Spectral refers to the spectrum, that is the number of bands in the electromagnetic spectrum that has been used to capture the image. Radiometric refers to the radiometry, that is the bits per pixel in which the image has been captured. So radiometry may refer to 8-bit image. 8-bit image means the pixels will range from 0 to 2 to the power 8, or 10-bit image, 16-bit image, 11-bit image, 16-bit image, and so on. Spectrum refers to the band. So red, blue, green, near infrared, thermal infrared, far infrared are all different types of spectrum in which the images of the Earth are captured. Finally, temporal resolution refers to the time interval between two subsequent acquisitions of images for a particular satellite. Okay, so now I will very quickly take you through a case study of Bangalore that we all know is the capital city of the state of Karnataka, and has been in focus because it is one of the economic powerhouse. People have migrated to this city from other parts of the country in the in for education, for jobs, employment, and so on. As such, the city has grown in almost all the directions. And to give you one example, we have grown much beyond our greater Bangalore boundary that is shown in the first figure. The second figure is the Google Earth image, corresponding Google Earth image, and the third picture shows the false color composite of a particular satellite, where we see some portion of the new Bangalore International Airport, Kempegowda International Airport, Bangalore, and some portion of Neelmangala. Here we see Hoskote, and at the bottom we see Electronic City and the Hosu Road connecting Jigni and Atibele, and also Chandapura, and then following that to Hosur. So IIIT Bangalore is located in Electronic City in this particular location. And we have one snapshot of a classified image, supervised classified image of Bangalore city taken from 1973. So here the red colors indicate the settlement area, the urban area, green is the vegetation, blue is the water body, and pink is the others category. And we see the transition in the urban areas from 73 to 92 to 2000 to 2004 to 2009 to 2014, and in 2014 and then in 2018 some of the things are very evident. For example, the electronic city area and the road leading to Hosur, the new airport with terminal 1 functioning and terminal 2 under construction, the Bangalore Pune highway, the Bannerghatta National Forest, IIC campus here, and so on. And this is the 2020 image where the terminal 1 and 1 is almost in operation and terminal 2 was under construction. And then again we see electronic city with new patches and other roads and other significant landmarks. This is our old airport with the runway. Okay, so this image in some sense summarizes the changes that have happened over the city from 1973 to 2018, approximately 45 years of gap, each color representing the change happened in those different years. So what is more interesting to us is the statistics that has been generated from these images. As an example, the city has for city has grown by almost 1794% in the last 45 years, and subsequently there has been a 66% decrease in vegetation and 3.22% decrease in water bodies. So for moving on, we went ahead and then looked at the city level road networks. Road networks typically, as seen from literature, are of four types. One is a mesh or grid type as seen here. Second is a tree type structure as seen here. Third is a hub and spoke type as seen in figure C here. And fourth is a linear pattern as seen here. So these different types of transportation networks are characterized or studied through some indices which are known as connectivity indices and some coverage indices. So typically from the length of the edges of the road or vertices, that is nodes, we can compute all these different indices, example alpha, beta, gamma, eta, and these four or road density, network density, edge density, and also our nodal graph density. So these connectivity and coverage indices tell us many things about what is the road pattern or how good is the road network in a given city. Taking example from this, we tried to study more than 500 cities across the country, and this work was presented at IGARS in 2023 in Los Angeles by one of our PhD scholars. And then subsequently, these road networks were used to the road network of the 500 cities were first divided into very low connectivity, moderate connectivity, high connectivity, and very high connectivity to see which cities have really good road network. And then these road networks were used to see which are the cities across the country that have potential to grow further given the infrastructure. So this paper was published in Nature Scientific Reports, and here I have just a very small snapshot showing you the city of Mysore in Karnataka, city of Mangalore, then Hubli and Belgaum and Gulbarga. So this here we had used something called GAN, GAN, GAN. GAN was used to simulate synthetic cities, and then we had used actual road network metrics to see how or what could be the new future cities in different parts of the country. And to be more specific, for Karnataka, we were seeing what could be the alternate cities if Bangalore has already oversaturated. So we looked at some of the other important cities which I just now named. Here are the road network for Mysore, Mangalore, Hubli, Belgaum, and Gulbarga to see whether these cities can really be the next growth or economic growth hub for Karnataka, alternate to Bangalore. Uh, I had talked about the term classification, and then I said that the term classification in satellite data is very important, and there is one problem that we often encounter, that is called the class imbalance problem. So in Bangalore city, for as such, we have only or mostly dominated by buildings or settlements. So buildings typically are present in major quantity, large quantity, and lakes, for example, are very few, or parks, for example, are very few, which are present as minority class. So this creates a majority class minority class problem, and any classification algorithm which is trained on such data typically tend to have biasness. So to overcome this problem, the idea is that how do we increase the number of samples for the underrepresented classes? So typically these are done by scaling, rotation, flipping, or noise adding, blurring, and so on. Recently, new trends have indicated that GAN, that is generative adversarial networks, and VAE, variational autoencoders, have proved to be very efficient for generating new samples that are very close to the original data in terms of structure and in terms of the distribution. So there is one algorithm that we have come up with called structure preserving variational learning (SPVL) that typically tries to solve this data imbalance problem, working on the minority class. And here is the one snapshot of that particular algorithm, and here is the detailed algorithm of how it works. How it how it tries to increase the number of sample for the minority class. Here are some results on some standard benchmark data sets. And we are still trying to transform this research to real world satellite data and see if this can address the problem that we encounter from settlement versus water or lakes that are typically imbalanced in nature. Okay, now I would like to move on to our next topic on subpixel classification, where the idea is to see why is the per pixel classification wrong. So in our previous case study for Bangalore city, we what we did is actually we assigned one class to every pixel, one class to every pixel. This is still fine as long as the pixel resolution is quite high, maybe few meters, 1 to 5 meters. But very often we realize that the land cover on any landscape do not actually follow the boundaries of a pixel, and therefore most land use classes are not spectrally distinct in moderate to low spatial resolution data. So what I'm trying to say is that let's see this particular landscape. We have houses here, we have a water body here, we have some lawn park here, and then there is some parking here. And one block is one pixel of 30 meter by 30 meter. So we realized that a 30 meter by 30 meter pixel can have a mix of water or some green vegetation or some settlement area. In a normal classifier, the whole pixel is assigned one class. So we realized that this particular pixel has dominant vegetation class V, the green color. So therefore, a normal machine learning algorithm will typically try to assign vegetation to this entire pixel, which is known as per pixel classification. But in fact, we see that this pixel has only 20% settlement, 60% vegetation, green cover, and only 20% water. So the idea is, how do you now separate these different classes from a pixel? That is, given one pixel, how do you separate the classes from that particular pixel? This physical you can say interaction can happen in two ways. One way, in a linear fashion, where we assume that sunlight hits the earth object, maybe buildings, parks, trees, and then reflects back to the sensor. Second one happens in a non-linear way, that is sunlight hits the building, then the reflected energy from the building hits a tree, and then the reflected energy from the tree hits an aeroplane, and then that light goes back to sensor. So this creates a non-linearity in the system. So now here we see two few cases of mixed pixel. We see object 1, object 2, and a background, 3 object in 1 pixel. Here we see mixing of 3 classes. This is class 1, class 2, class 3. Or another simple example could be a road, a 2-lane or a 4-lane road, which is part of a pixel. So the question is, how do you then solve this particular problem where I have to separate out classes from within a pixel? Okay, so the basic formulation is perceived as follows. Assume this particular pixel to be 1 pixel having 3 classes, 3 mixed classes, and let's say this pixel value is intensity value is y. So we define y is equal to reflectance of class 1 into area of class 1. So this is my area of class 1 plus reflectance of class 2 into area of class 2 plus reflectance of class 3 into area of class 3. So this is what is shown in this particular equation. We add two constraints to that. One is, please don't allow any class to be negative. I cannot have, for example, I cannot have minus 20% water. And second constant, if you add up all 1, 2, 3, it should become 100%. Okay. So traditionally, this particular problem was solved in the year 1991 to 1993 by one of the approach called ordinary least square. Here, the idea is to minimize the difference between the reflectance of the pixel and the EA, that is n member reflectance, and the area of that particular class. So we saw that the estimate of that of any class is obtained using this particular equation, using the ordinary least square method. For a very long time, this method was used for solving the mixed spectral problem until in 1999 and close to 2000. A professor from University of Maryland from the electrical engineering department, Professor Chang I Chang, he came up with a technique that was motivated from signal processing. This technique is called orthogonal subspace projection. So here he treated a satellite pixel value as a signal, as an electronic signal, and then applied a model called DU model. So the DU model, D means desired class, U means undesired class. So what he says is, treat one class at a time. So if building is my class, it is desired, and then vegetation, water will become undesired. And then he tries to maximize the signal to noise ratio, and then come up with a very nice equation where alpha is my proportion of a class in a given pixel. So alpha is the proportion of the pth target material, pth class in a given pixel. Okay. So now I will just go back to our original formulation and then show that till very recent time, the uh, the um, the approach proposed by Professor Shiv Maraku from I think from Brazil was the only method to solve this problem, and this was the alpha equation that was used to estimate the fraction of, this is fraction, alpha means fraction, proportion of a class in a given pixel. Okay. Now, if things become non-linear, that light hits the building, then the tree, then the aeroplane, and so on, it creates a non-linear mixture problem within a pixel. And here I'm just showing you one of the approach that we proposed, was published in Information Journal, where we used neural network, multi-layer perceptron, to address this problem of non-linearity. And this is a small flowchart. I can definitely share the paper if interested. And this is the architecture of the MLP model and the structural diagram. And let's now show you some pictures. So in order to test the methods, we downloaded the signature, the spectral reflectance of 4 minerals: alunite, budagonite, kalonite, and calcite from Jet Proportion Laboratory. And using those signatures, we did some computer simulation. So using simulation, we generated 200 synthetic bands that should mimic satellite images. Okay, this was the model that was used to simulate synthetic images, and then subsequently used both linear model and non-linear model to separate the four minerals: alunite, budagonite, kalonite, and calcite. You can see this is the actual classified image, and this is the linear model, this is non-linear model, and with graphs also. The by the graphs at the bottom also reveal that yes, non-linear models typically outperform compared to linear models, because linear models make the composition understanding very simple. Subsequently, the same technique was applied on small part of Bangalore city. To give you some context, this is the race course here. This is the Majestic railway station with bus stand and the railway lines close to that. And then we have four different resolutions at 1 meter, 4 meter, 25 meter, and 250 meter. And then we apply both linear and unlinear mixing on those data with two class problem and with three class problem. Okay, one thing to observe, that if you have two classes, we get two outputs. Why two outputs? Because one
Sir,
class, one,
excuse me, sir, sorry to
yeah, please
intervene
go.
here.
Yeah,
Actually, we are far behind the scheduled time. So, if you could wrap up in few minutes.
I'm unable to hear you.
Uh, Actually, we are far behind the scheduled time. So, could you please wrap up as soon
Okay,
as
okay,
possible?
okay, okay, okay. I will try
Sorry.
to wrap
Yeah,
up.
yeah,
Right.
yeah. Thank you,
So
sir.
here
Thank
are,
you.
yeah, sure. Within 5 minutes, I will wrap up. Okay, so here are three different outputs for each one of the class, and here is one real world case study from close to our international airport. Here is the Nandi Hill, and here is the Chikbalapur town, where we tested these particular techniques. Okay, and these are some graphical output of the errors that we saw in each class, and correlation metrics and between the linear model and non-linear model for each of the class, which also indicated that non-linear model typically works better in such scenarios. So this was the finding that I have just now emphasized, both related to simulated data and for the unmixed for the real world data. Okay, I will skip some part because this will require some more discussion, and we can take it anytime further. This paper typically tried to differentiate different type of same materials. For example, concrete building, or building made up of mud, or building having plastic roof or tile roofs. So how do you now differentiate between these different buildings that belong to the same class buildings? So I will skip some of these parts, which we can definitely talk about later. Quickly show you some of our implementation on big data, where we now realize the importance of multiple satellites being launched and collecting large amount of data, and creating several challenges related to data volume, data access. How do we create scalable processing systems, and how do we make the systems analysis ready? So currently, to give you one example, we have climatic data that has exceeded 350 petabytes today, that gathered from the different remote sensing satellites, and multiple applications including global forest cover, global vegetation cover, global precipitation measurement, and so on, are being addressed through these particular large scale data sets. So the subpixel classification task that I had shown has now evolved, and different methods including sparse unmixing, signal subspace projection, geometrical projections have also come up, have been proposed, that tend to work very nicely. Here is our contribution to the method that was able to speed up this particular technique for being implemented on the entire globe. And you see here in this particular picture the training data being collected from across the globe, across the continent, across the countries, related to three different classes. So this is the global NDVI from our experiments, and this is the global mosaic of 8,003 scenes, pictures of the satellite images across the globe, with six spectral dimensions, total resulting in 224.3 billion pixels in six dimensions. This is the flow chart that is documented in the paper, and is quite straightforward using high performance computing. And these are some results of the classification. The paper was published in Remote Sensing as shown here. And this slide talks about the validation steps of how these large scale data sets were validated. And we had also used some of our high performance computing to classify individual trees using high resolution satellite images. And here are some examples taken from San Francisco, and here, and this is the Golden Gate Bridge, city of San Francisco, and this is the state of California with the tree cover, and this is the tree cover across the US showing their percentage obtained using CNN. And this is already I have outcome. I have highlighted. This method was actually 6% better than the state of the art. Okay, now I will very quickly show you some small case studies. This work was related to pothole detection in electronic city phase 1. So we collected data on dry days and also rainy days across this particular region, and developed a model that could be mounted on a car, and the following video will show you prediction of potholes when you move on a car and keep this mobile mounted on the dashboard. So any upcoming pothole would be immediately shown to the driver. There were some false positive. For example, the garbages kept on the roadsides sometimes also got classified into these potholes. And I have another video there where we see this particular application. This place is very close to the Hosur Jigni highway. So this is another small video showing you how the potholes were detected using AI with respect to mobile photographs or mobile videos, and how this has been automated to be used in a real world scenario. Okay, some work has been done using the UAV drone data, where we have worked on tree canopy detection and tree counting using AI related techniques. So here are few scenes showing you drone images. This is the overall methodology in divided into two stage, and here are some results. The red box basically indicate the output from our model, and the black box represent the ground truth. And this is the final output. You can see this is the actual RGB image. Uh, this is the actual RGB image, and sorry, just hold. Yeah, this is the actual RGB image, and this is the final where the tree canopy has been extracted, removing the shadows of the tree and also the underlying soil of that particular tree. In this work, we try to segment the high transmission power cable from the images taken by drone. And one big challenge was how do we classify things that are in minority classes. The cables, for example, are in minority classes. So here are some results of power line detection. And here are some examples of crop classification, UAV drone images. This work is under progress, where we are also looking into plant disease detection taken from mobile photographs. Here are some pictures of some diseased leaves of different plants. And I will now try to summarize by just highlighting some of the challenges. Currently, even we have some data sharing challenges, and moving larger data from one platform to other is still something that we need to resolve. Sharing of codes, intermediate results, workflows is still difficult. As such, there are many new interesting areas that we can continue to work on and collaborate, including the recent trends in machine learning, crop yield estimation, precision farming, deforestation. And in the field of digital agriculture, we have some work done with ISRO, and we are looking into tomato plant yield estimation and sunflower yield estimation, which is used to obtain sunflower oil. And lot of interesting research still remains in hyperspectral image processing and Google Earth engine that typically provides 5 million approximately, sorry, 0.5 million satellite images from across the globe that can be used to study land cover change, surface temperature, climate change, and so on. Two more slides to go. Class incremental learning and domain incremental learning is something very new to be addressed, where the idea is to have increasing number of classes with respect to time, and can we have a model where which can work if the number of classes increase, and then can we have a model that can work where that is developed for one place can be adopted to other place. So we develop a model for Bangalore city and can we use it for Mysore city. This is called class incremental and domain incremental learning. Good amount of work is currently going in 3D GIS, where simulation models using AR, VR are being developed and currently being used in many applications. For example, real estate also, where you see your apartments, your flats, even before they are constructed. Even the interior decorations, interior designers are using it to give you some visuals of how the flat will look like once the interior design is over. So with this, I would like to acknowledge my supervisors, my collaborators who have helped me, and worked with me throughout my journey. And thank you for being here. I would like to heartfelt thank each one of you for being here for another last 1 hour. And thanks to our team, Namrata, who was in constantly touch to arrange this talk for you. Thank you very much. I'm ready for any questions that you would like to ask. Namrata, I'm done. Any questions?
Um, yes, yes, sir, Linda is taking that forward.
Yeah, sure, sure, sure. Yeah.
Yeah, we now welcome the audience to ask any question. Please unmute yourself, or you can also post your questions in the chat. So maybe audience are quite hesitant. Maybe if I start, they might start asking. So I have like very two, three questions for you. One of the application that stood out for me is predicting new city using hybrid ridge gun.
Yes,
So
yes.
what is the factor that is given in it? It is completely based on transport, or any other driver variables were also introduced as part of modeling.
Okay, here we were looking into the yes, of course, one of the parameters was what is the current road network that would be able to suffice the expansion. I mean, if the number of people population increases, there is more requirement for expanded roads. Will the current infrastructure will be able to cope up with that? And do these cities have outer regions where the expansion can continue? So taking these two factors, we try to see what could be the new future cities where that can provide you not only the road network facility but also land outside the city to have new construction activity. Although we can keep adding other parameters, for example, electrical connectivity or water supply, but these two were the initial two parameters to judge if a city can be taken up as the next economic hub for expansion. Given that currently government of India has enough interest in trying to develop our tier 2 and tier 3 cities as the new hub of economic activities.
Thank you. And one of the work was differentiating building based on the building material itself.
Yes, yes, yes.
So, in my work, I have faced a challenge where I have to classify building as well as mining area. So, I was working with medium resolution data. The
Mhm.
spectral reflectance of both the features seem to have similar reflectance. So, which approach do you suggest to differentiate these two features in particular?
Okay, so you are right. So typically, what happens in a supervised classification, for example, there is a high chance that in Bangalore city, I would say, to give you some relevance, There are queries, stone queries. When we moved from Hebbal to the airport, on the left side we see some large quarries, that is hills that are being digged up, and the stones that are being used for construction activity. So these quarries appear very similar to buildings, and when we do any such sort of classification, these quarries get classified as built-ups or settlements. Even some of the lakes that have dried up, and instead of water they have some soil at the basement. These soil reflectance look very similar to the building construction. So in that particular work, our objective was to see that the intra-class variability in the sense, the variability within the subclasses of a class. As such, buildings, different types of buildings; water, different types of water, could be clear water, turbid water, and so on. So how do we increase the interclass variability to differentiate these subclasses within a class? This was our purpose, and we try to address this problem using one of the proposed method which was discussed in that particular paper. In this is slightly easy when we look at the sub-pixel classification, but at a per pixel classification, this problem is slightly more dominant, because because of the resolution of the pixel, which is not enough to segregate subclasses within each class. So this could be one reason for the confusion. Even we have faced this particular confusion. Subsequently, we have used some ground truth and did some manual encoding to overcome this separation problem.
Okay, okay, thank you, sir. And one last question, which is general. So, what is your perspective on the tendency to use these machine learning techniques just to showcase sophistication rather than to solve the problem, especially when the entire crowd is marching towards Geo AI?
I think machine learning are very nice tools to solve many of these problems that require complex processing. Uh, However, we should realize that they are only tools and cannot completely substitute a GIS expert. As such, always the domain knowledge or any human in the loop is required to interpret these subjective things in earth sciences, for example climate change, or as you rightly pointed out, the last example where we have class confusion between similar types of classes, buildings made up of different materials. So machine learning models work very nice as automated tools, and tend to learn very well on the developed training data by a expert GIS user, or by any data analyst who is good in data interpretation. So usage of ML is definitely justified, but rightly supported by expert opinion or expert user with their interpretation capabilities. This would be my takeaway.
Okay, thank you. So we have one question in chat if you could answer. Question is from Vijay.
Yeah, please go ahead.
So the question is like, if thermal signatures could simplify the problem of classification where multiple classes exist in a pixel.
Yes, definitely, and there are some of our approaches where we have integrated thermal bands because they significantly impact the separability of classes. As an example, thermal range, or you can say temperature of maybe different types of urban forest are different. So if you compare Benegata National Forest to, let's say, Lalbagh Garden, they are quite different. So because of the variation in the thermal index, we are able to separate these minor differences between or within the classes. IIC used to have very dense forest till we were doing some of our case studies, and until even now they have some of the very rich forest areas. So typically we see, even one of our own study done at IISc has shown that the temperature within IISc campus used to be approximately 2 to 3 degrees lower compared to the neighborhoods, compared to the surroundings. So obviously, this temperature variation helps us have very clear to have very clear discriminative capabilities with respect to class separation, or with respect to differentiating two different similar looking classes. So I would definitely suggest to bring thermal bands as part of the input data while doing classification task.
Thank you, sir. So, since we don't have any more questions, it's the conclusion of the session. Thank you once again, sir, for graciously sharing your expertise and for an outstanding session that offered depth and clarity on data analytics, role of GIS, geoinformatics, machine learning in geospatial data processing, handling big data, and so on. We truly appreciate your time, effort, and thoughts you have invested in making today's session, sir. Thank you. And our sincere thanks to the participants for joining the session and for your active engagement through your questions. With that, we come to the close of the session. Have a pleasant evening. Thank you, everyone.
Thank you very much. Thank you, Namrata.
Thank you, sir. Our pleasure to host here.
Yeah, thank you so much. So can I now log out,
Yes,
leave the
sir.
meeting? Yeah,
Yes, sir.
thank you so much. Thank you so
Thank you
much.
so much, sir.
Thank you, Linda. Thank you so much.